Mass spectrometry is a technique which is used to find out the molecular weight. So, molecular weight or the molecular formula of a compound, right? It's quite different from the other spectroscopic techniques like infrared spectroscopy, NMR spectroscopy, where we allow the interaction between matter and electromagnetic radiations, right? So, here in mass spectrometry, there is no involvement of any electromagnetic radiations in mass spectrometry, right? So what we do in this, suppose we have an organic compound, and we vaporize the organic compound, right? And when it is vaporized, then we allow or we bombard a beam of high energy electrons, 170 electron volts. This is called electron impact ionization. We'll see why it is called so. So when you allow these high energy electrons to come in contact with the atoms of organic compound, these high energy electrons, they knock off an electron from the atom of that organic compound and convert it into ions, right? So step 1, you vaporized it. Step 2, you allow the interaction between that organic compound with the high energy electrons, which causes ionization, and we get ions. And then we accelerate those ions in a path, which are then passed through a magnetic field. So we have magnets here on both sides, magnet. So these are ions are passed through this magnetic field, and then they are detected by a detector, which convert that into a graph or a chart, which we'll explore a minute later. We'll explore this. So when these ions are passed through the magnetic field, they get deflected. Not all the ions are deflected to the same extent. So it's like the heavier ions, like the one with the bigger mass, they are deflected the least, right? And the lighter ones, like with the small mass, they would be deflected the most. They're most deflected. Just the way, like if there is a heavy wind, the lighter things would be disturbed, they're more prone to get disturbed as compared to the heavier things. In the same way, this happens here. At the same time, these ions also carry charge, suppose a positive charge, right? So the ones with the bigger charge, say +2 charge, they would be deflected more as compared to the one with the lesser charge, right? Now we'll see how the things happen. Suppose I have a molecule XY, right? It is vaporized, and then I bombard it with a beam of electrons, beam of high energy electrons, like high kinetic energy, right? Then that would knock off one of the electrons from the bond between X and Y. And what I would get a species which is called radical cation, right? So this is called a radical cation, and the electron is knocked off. So one of the electrons, so just for the sake of understanding, I'm writing it like this electron is suppose knocked off, and what we are getting is a species which is called radical cation. Radical cation, because there is an odd electron and there's a positive charge, so it's called radical cation. And we know that the mass of electron is quite low, so it means that the mass of the radical cation is the same as the mass of the starting molecule, right? Now let's take the example. Now this radical also I want to highlight that this radical cation, it is not very much stable, and it can undergo further fragmentation to produce more cations, And depending on how many cations are formed, we can get a graph which is called mass spectrum, which looks like this, that on um vertical axis we have relative abundance, and on this horizontal axis we have the mass to charge ratio, of the ions which are formed, right? Most of the time the charge is plus one only, so mass to charge ratio, it represent mostly, you know it represents the mass of that particular cation, right? Suppose from X, this radical cation, I get different types of ions after fragmentation, A ion, B ion. Now depending upon how many of them they are there, I would get, peaks or sticks, like stick diagrams like this. This is just a hypothetical example, so the tallest of them, that is called the base peak, and we assign it as if its relative abundance is 100%. This is hypothetically, we define that the tallest one is 100%, and relative to that we define the abundance of other cations, right? Now let's do this with an example. So let's take the example of the simplest molecule, methane, right? You vaporized it and then you allow it to, come in contact with a beam of high energy electrons. High energy electrons, it's like you pass. Okay, we covered that. So now what this would take away, it would take away one of the electrons out and we get a radical cation, right? This is our radical cation. It has the same mass as that of the parent molecule, radical cation, right? Has the same mass as that of the parent molecule. The mass of the parent molecule is 16 grams per mole, so the mass of the radical cation would be the same as this one. It's quite unstable. It can undergo fragmentation. The type of fragmentation can happen. So I have this thing and it's undergo fragmentation. What I can get one cation like this one plus the hydrogen, right, as with the odd electron. So the mass to charge ratio for this would be 15, right? Mass to charge ratio for this was 16, right? This can further undergo fragmentation to give us, I'm just showing it here, like CH2 positive, right? And with the same process and all that. And the mass to charge ratio for that would be 14, right? So if I show you the mass spectrum of methane, the mass spectrum of methane is this one, right? Let me enlarge this one. Okay, so if we see here, so this is our base peak. This one. This is base peak. Base peak is the peak which has a relative abundance of 100%, or which is the tallest peak, right? So this is the base peak. Since its relative abundance or relative intensity is the highest, it means the species corresponding to this M/Z ratio is present the most, right? And what is that species which has a M/Z ratio of 16 from the mass spectrum of methane? It is this species, the radical cation, has a mass, right? So this is it. Next one is this one. It corresponds to this cation, this one, right? Next one is this one, right? And then next one is, you have this only, and then just the carbon atom, right? So this is the mass spectrum of methane, which is the simplest molecule. This is the base peak. This base peak also represents the molecular ion peak. Like this is the peak which corresponds to the molecular ion, the main ion, which is formed just by the knocking off one electron, if we can see here. So this is not only the ion corresponding to the base peak, this is also called the molecular ion, right? Molecular ion is generally represented as this M, and you have a positive, and this is the depiction of a molecular ion, right? So base peak is the tallest peak, but that tallest peak or the base peak who can be a molecular ion cannot be a molecular ion. Sometimes a molecular ion is very much unstable and it ionizes very easily, it doesn't its lifetime is too small, so the molecular ion keeps on undergoing fragmentation to give more and more of the daughter ions in that sense, right? So we can also see that there is something, if you see at this, right? We call this M+1 peak, and we'll see where from it is coming. M+1 peak, right? So this was about the principle of spectroscopy, about how to interpret the mass spectrum. On mass spectrum, on y-axis or vertical axis, we have the relative intensity or relative abundance. And on horizontal axis, we have M by Z ratio, where M represents the mass of that ion and Z represents the charge of the ion. Most of the time, charge is 1, so M by Z ratio essentially represents the mass of the species, charged species or ions, right? That's all for this lecture, and we'll continue with more on mass spectrometry in the subsequent lectures. Thank you.